Welcome. Mrs. Greathouse here. We're kicking off Chapter 10 by learning about moles. In the fall, we talked about moles being a basic unit of chemistry measurement. Now you're going to learn exactly what's a mole. A mole is just a measurement of matter. It's going to help us quantify a large number of small particles. Okay, imagine you built this sand castle for a contest on the beach, and one of the requirements was you had to report out how many grains of sand were in your sandcastle. Do you really want to count every grain of sand, or would you rather measure a gram of sand, count the number of particles in that, and then measure the mass in your whole sandcastle and use that number of grains of sand per gram as a conversion factor to mathematically find out the number of grains of sand in your castle? Okay, moles work in a similar fashion. Okay, we have different ways of measuring things. We can measure by count, by mass, or by volume. If we are talking about the screws, we are most likely to count them. If we are looking at the bag of birdseed, we're most likely to take a mass. It would be tedious to count every little seed. If we're looking at a liquid measure like the paint, we are most likely to use volume. Okay, with moles we can incorporate all of these three concepts as well, and we'll do that day by day. Okay, for example, how can we find the mass from a count? Okay, here's our question. What is the mass of 90 average sized apples if 1 dozen of the apples has a mass of 2 kilograms? Okay, we know that 1 dozen is 12 apples. So we can set up a ratio. 12 apples is to 2 kilograms as 90 apples is to x. We're going to cross multiply and divide, and x equals 15 kilograms. Okay, we are going to work with moles in a very similar fashion. Okay, so what is a mole? A mole of a substance is 6.02 times 10 to the 23rd representative particles. It's our SI unit for measuring substance. It is a measure like a dozen. A dozen is 12 eggs or 12 apples. Okay, if we talk about a gross of pencils, it's 12 times 12, 12 dozen, or 144. Okay, it's just a number for a large number of particles. Okay, this number, the 6.02 times 10 to the 23rd, how many particles make up a mole, is called Avogadro's number. Okay, when we use this in dimensional analysis, our conversion factor is going to be 1 mole over 6.02 times 10 to the 23rd representative particles. Okay, we can use that as written or flip-flopped, either way. But this allows us to, as in dimensional analysis, we can cross off the units that are the same on the top or the bottom, okay, and we can get our answers in moles. Okay. So here's your key point. A mole of any substance BATS contains Avogadro's number of representative particles, or 6.02 times 10 to the 23rd representative particles. What's a representative particle? Okay, that's going to be atoms or molecules or formula units. Okay, formula units just refers to the chemical formula of a compound. Okay, in the yellow box a couple slides ago was an example how we can convert moles to representative particles by dimensional analysis. I'm also going to teach you how to do this by algebra. I want you to know two ways because sometimes when you get to college, your professor knows one way or the other, but not both. So I want you to be ready for that. This is your formula for figuring out the relationship of moles and representative particles with algebra. A mole equals representative particles, we're going to abbreviate that as RP, divided by 6.02 times 10 to the 23rd. Okay, so who was Avogadro? Here's his picture. He was an Italian scientist that lived from 1776 to 1856. The majority of his work was focused on clarifying the difference between atoms and molecules. Okay, other scientists named 6.02 times 10 to the 23rd after him in 1909. Okay, this chart is in your book. Okay, it shows us that no matter what type of particle you have, atom, molecule, ion, formula unit, the number of representative particles in that mole of substance is always 6.02 times 10 to the 23rd. Okay, so let's try a conversion. We need to find out how many moles of magnesium are in 1.25 times 10 to the 23rd atoms of magnesium. We're going to do this first one by dimensional analysis. Okay, so here's our 1.25 times 10 to the 23rd atoms. That's where we start. We need to end up in moles. We need to multiply by our conversion factor here, which is going to be 1 mole over 6.02 times 10 to the 23rd atoms, or we could write RPs there. Okay, we're going to cross off like terms on the top and the bottom. Okay, multiply across the top, multiply across the bottom, and divide. So then our answer is 0.208 moles of magnesium. Okay, remember, when we're doing this on our in-class calculators, we need to use parentheses. Okay? Alright, so let's try the same problem by algebra. This is our formula, moles equals RP divided by 6.02 times 10 to the 23rd. Okay, so we're going to plug our RPs in there. So moles equals 1.25 times 10 to the 23rd divided by Avogadro's number. Divide, and we're going to get the same answer, 0.208 moles magnesium. Okay, so what if our problem says convert from moles to number of atoms? We're going to use the same thing, just rearrange a little bit. Here's bi-dimensional analysis. We have 2.12 moles of propane that we need to convert to RPs. So we're going to use that same conversion factor, but this time moles goes on the bottom so that we can have our answer in RPs. Okay, cross off moles. Multiply across the top will be dividing by 1. So our answer then will be 1.28 times 10 to the 24th representative particles, which are going to be molecules of propane. Okay, so let's try the same problem by algebra. Here's our formula, same one. This time we're going to plug moles into there. So it's going to look like this. I've got to multiply 6.02 times 2.12 to solve for, that'll get representative particles all by itself, and my answer will still be 1.28 times 10 to the 24th RPs. Okay, next we need to talk about the mass of a mole. Reach all the way back to atomic mass in chapter 4. Okay, where we looked at the atomic masses of a compound on the periodic table and figured out how many were there and added them all up to find the atomic mass of an element. Okay, there is a relationship between this atomic mass and the mass of 1 mole. Okay, atomic mass is expressed in grams, and that is the mass of 1 mole. Okay, we are going to call this molar mass. Its units are grams per mole. Okay, atomic mass is the same as molar mass. And we're going to use this more tomorrow, but I'll tell you how to calculate it today. This should all be review. I love this picture from your book because it shows you 1 mole. Okay, if we look at a mole of carbon atoms, its mass is going to be 12 grams. Okay, what's the atomic mass of carbon? 12. Okay, same with sulfur. A mole of sulfur is 132.1 grams. What's the molar mass of sulfur? What's the atomic mass of sulfur? 32.1. These are the steps to calculating molar mass, same as atomic mass. We'll do an example next. So if we need to find the molar mass of sulfur trioxide, okay, we know we have 1 sulfur atom and 3 oxygen atoms. We use our periodic table to find the atomic mass / molar mass of sulfur and oxygen. Okay, we find that sulfur has an atomic mass unit of 32. Oxygen is 16. We have 3 of those. We could just go 16 times 3, and then we add everything up to find our molar mass of sulfur trioxide. Okay, so let's practice. Let's find the molar mass of hydrogen peroxide, H2O2. We know from our subscripts that we have 2 hydrogen. If we look for the atomic mass of hydrogen on the periodic table, we find out that it's 1. Okay, so we have to add that to the atomic mass, molar mass of oxygen. We know from our subscript that we have 2 from the periodic table. We know its AMU is 16, so 2 times 1 is 2, plus 2 times 16 is 32, add those together. 34, 34, 34 grams per mole. See you tomorrow for practice in class.